everybody. The purpose of this video is to go over the first part of section 1 in chapter 6, which is entitled The Greatest Common Factor of Two or More Terms. In this section, we are going to talk about prime numbers, prime factorization, and we're going to use prime factorization as a tool to find the greatest common factor of two or more terms where that term may contain not just integers but also variables. Okay, so what is a prime number? Well, an integer happens to be a prime number if 1. It has exactly 4 factors, and 2. Those 4 factors are, well, the negative version of an integer, negative a, negative 1, 1, and a. Negative a and negative 1 are factors because negative a times negative 1 actually produces a. So that's it. If it meets these two requirements, it is a prime number, and if it doesn't, it is not a prime number. For example, 1 is not a prime number. Why? Well, or also is negative 1. Why? Well, because both of those terms have exactly 2 factors, negative 1 and 1. So since it does not have enough factors, this is not a prime number. So then what are examples of prime numbers? Well, how about, here comes 2. The factors of 2 are negative 2, negative 1, 1, and 2. So 2 is indeed a prime number. As a matter of fact, it is the only even prime number because all other numbers have 2 all other even numbers has 2 as a factor. Accordingly, 3, 5, 7, and 11 are prime numbers, as is 13. The factors of 13 are negative 13, negative 1, 1, and 13. As a consequence, it is a prime number. However, 12 is not a prime number. Notice that the factors of 12 are negative 12, negative 6, negative 4, negative 3, negative 2, negative 1, 1, 2, 3, 4, 6, and 12. All of these are factors of 12. Is negative 6 a factor of 12? Of course. Negative 6 times negative 2 is 12. Therefore, it is a factor. Okay, and we want to use prime numbers as a technique that we call prime factorization. One large result of a discipline called number theory is this idea of prime factorization. And basically the idea is that any integer a can be represented as a product of prime numbers, and that is what we would call the prime factorization of a. Moreover, the prime factorization for any number happens to be unique. If a and b are 2 different numbers, then they will indeed have 2 different prime factorizations. So let's look at a couple of examples. Here is 2. The prime factorization of 2 is, well, since 2 is a prime number, its factorization is, well, 2. Similarly, the prime factorization for 13 is, however, the prime factorization for 12 is 2 times 2 times 3, or 2 squared times 3. Now, how would we come up with that? Let's look at all the factors of 12. Or let's take 12 and write it into 2 factors, such as we know that 12 is equal to 4 times 3. There we go. Okay, that's supposed to be a 3. Okay, well, that's cool. Well, in that case, 4 times, but 3 is a prime number. That's supposed to be a 3. 4 is not. So we can rewrite 4 as 2 times 2. And then we'll have the 3, and there is the prime factorization of 12. Similarly, we could rewrite 12 as 2 times 6. Well, 6 can be factored into 2 times 3, so that would be 2 times 2 times 3, which will be 2 squared times 3. So no matter how you start off your initial factoring, you will come to the exact same result. And then finally, the prime factorization of 90 is this down here, but how would you arrive at that? Well, take 90 and we can write it into 2 factors. How about 9 and 10? 9 times 10 is 90. Okay, well, 2 factors, these are not prime numbers, so we're not done yet, but the factors of 9 will be 3 times 3, both of which are prime numbers. And the factors of 10 are 2 times 5, both of which are prime numbers. So when we when we sort them into order, which is not necessary, we'll have 2 times 3 times 3 times 5, which is what we have below. So that is the prime factorization. That is how we can compute the prime factorization for a variety of numbers. So we are going to use prime factorization to come up with the greatest common factor for a set of terms. And we're going to use this as a guide as we go through a handy dandy 4-step process. Okay, and here is step 1. First is to write the prime factorization for all integers and integer coefficients. And this is what we have here. The prime factorization for 6 is 2 times 3. For 18, it is 2 times 3 times 3. And 21, since the only factors there are for that one are 3 and 7, both of which are prime, that's what we have. Step 2 is to list all the factors that are common, including variables. Well, each of these terms has a 3. Here it is. So we listed it there. Each of these terms has an x right there. So we have an x. And finally, each of these terms has a y. So we have a y. No powers, just the x's and the y's. Then for step 3, we want to choose the greatest power for each factor that is common to all the terms. Or a better way to look at it is we want to count the number of x's and y's that are in each of the terms. For example, here in the first term we have 1x. The second term we have 2x's, but the third term we only have 1x. So each of these terms has exactly 1x in common, which is kind of like x to the first. Now for the y's, and that's why we have a 1 here. For the y's, we have a y squared here, a y squared here, and a y squared there. So each of the terms has a y squared, so a y squared right here is common for all the terms. And then finally, we want to multiply the factors and powers and multiply the factors and coefficients to find the greatest common factor. Notice there's nothing here to multiply. As a consequence, this right here is the greatest common factor for these 3 terms. And notice that it consists not just of coefficients, but it also consists of variables. Okay, so now it is time to put this thing to the test. So let's go ahead and do that. Here we have the greatest common factor. You want to find the greatest common factor of 42 and 20. Well, to find and our first step is to find the prime factorization. So for 42, the factors of 42 would be 6 and 7. 7 is a prime number, 6 is not. 6 can be factored into 2 times 3 times 7. So that is the prime factorization for 42. 2 times 3 times 7. What about 20? Well, 20 can be written as 4 times 5. Okay, 5 is a prime number, 4 is not. That can be rewritten as 2 times 2 times 5. And that is the prime factorization for 20. Kind of wrote it backwards there. Okay, next is to write down the common factors. Well, there is only one common factor. We have a factor 2 here and a factor 2 here, so we are going to write down a 2. We have a 3 here, but there's no 3 here. There's a 7 here, but no 7 in the second term. There's a 5 in the second term, but it's not in the first term. And there's only 1, 2 in the first term, so we can't put 2 down twice. So this right here is the greatest common factor. There's nothing to multiply, and there was no exponents to count for the variables. Okay, what about B? Well, B is just a rather more elaborate version of A. Here we have 12, 28, and 40. Well, the prime factorization of 12 is 2 times 2 times 3. 28 is 4 times 7. 7 is a prime number. 4 can be factored into 2 times 2. Sorry, times 7. And then here we have 40, which is 8 times 5. 5 is a prime number, but 8 can be factored into 2 times 2 times 2 times 5. And now for step 2, we want to combine the factors that are common. Notice we have a 2 here, a 2 here, and a 2 here, so we can write down a 2. And we might want to X out the ones that we just did so we don't include them twice. So that one is out, that one is out, that one is out. And notice here that we have another 2, and another 2, and another 2. So we have 2 2's that are common. So that'll be 2 times 2. And then we can line these out. Okay, there's a third 2 in the third term. There were no additional 2's in the first 2 terms, so that 2 is out. Here we have a 3, but that's the only 3 in any 3 terms, so that's out. Here we have a 7 by itself, and we have a 5 by itself. So it turns out in this case, the prime factorization for these 3 numbers is going to be 2 times 2, or 4. Which kind of makes sense because we have 12 divided by 4 is 3, 28 divided by 4 is 7, and 40 divided by 4 is 8, none of which have common factors. Okay, for C, we have 3x squared and 21. Okay, well, the prime factorization for 3 is 3, so that's pretty simple. But you can just write down to 3. X squared, we want to include the x squared, and then the prime factorization for 21 is 3 times 7. What do they have in common? Well, the only factor that is in common is the 3. We can't include the x squared because there's no x squared here. We cannot include the 7 because there is no 7 on the other side. So as a consequence, the greatest common factor is 3. And then finally for D, we have 35x squared, 49, and 10. So the prime factorization for 35x squared is going to be 5 times 7. X squared. The prime factorization for 49 is just 7 times 7. And then prime factorization for 10 is going to be 2 times 5. Now notice that we have a 5 here, but there's no 5 in the other term, so 5's are out. We have a 7 here and a 7 there, but no 7 over here, so these 7's are out. And then we have a 2 here, but we have a 2 in the third term, but no 2 in the first 2 terms. And we have an x squared in one term, but no x in the other one. So there are no common terms here. As a consequence, the greatest common factor, well, no common factors that are not 1. The greatest common factor here is going to be equal to 1. Greatest common factor is equal to 1. And why is that the case? Because 1 times any number will produce for you that number. So therefore, 1 is basically the universal factor. As a consequence, 1 is the only factor for these 3 numbers. Okay, and that brings us to the next collection of problems. Here we have 88 times and 8xy squared and 24xy. So the prime factorization for 88 for step 1 is going to be 8 times 11. Okay, 11 is a prime number, 8 is not. That can be written as 2 times 2 times 2 times 11. 8xy squared, well, the prime factorization for 8 is 2 times 2 times 2. Then we have xy squared. And then finally, the prime factorization for 24 is going to be 8 times 3, where 8 is 2 times 2 times 2. So this will be 2 times 2 times 2 times 3 xy. Okay, cool. Now we need to write down the factors that are common. Now notice that each term has 3 2's in it. So we can go ahead and write those down. 1, 2, 3. This term has an 11, which is unique to this term. This term and this term has an x. This term does not. We have a y and a y here, but no y over here. As a consequence, none of these are terms, and none of the variables are included in the terms, and we have 2 times 2 times 2. Since we have no variables, we can exclude step 3 and we go straight to step 4 by multiplying these out, which will give us, you guessed it, 8. And this is our greatest common factor. Okay, next we have 3x squared y and 9xy. Well, we don't really need to do too much with the 3x squared y since 3 is already a prime number, so we'll just write that down. And then the prime factorization of 9 is 3 times 3 x, y. Okay, and now we need to collect the factors that are in both terms. Notice that each term has a 3, so we write a 3 down. Notice that each term has an x, so we write an x down, and each term has a y, so we write a y down. Okay, now the first term has 2 x's. The second term only has 1 x, so there's only 1 x in common, and both terms have exactly 1 y. For step 4, there's nothing to multiply, so this right here is our greatest common factor. Okay, for 3, we have basically a more involved version of 2. We have 9xy, and its prime factorization is going to be 3 times 3xy. 3xy, and since 3 is a prime number, we can just go ahead and write that down. And then 6xy, which is going to be 2 times 3 times 6. 2 times, let me rephrase that, 2 times 3 times x squared. There we go. Those are the prime factorizations for our 3 terms. Now we can take a look and see what's common. Each term has at least 1 3. Well, actually, each term has at least 1 3. The last 2 terms have exactly 1 3, so we have 1 3 that is common. What about 2? We have a 2 here in the third term, but no 2's in the first 2 terms, so that's out. In the first term, we have a second 3, but there is no second 3 in the other 2 terms, so that one is out. Each term has an x. None of the terms have a y. Now, in the first term, we have 1x. In the second term, we have 2x's. In the third term, we have 3x. So that basically means that they each have 1x in common, and that gives us our greatest common factor, which is 3x. Okay, next is this one. Kind of running out of space here. Let me just change colors so it's clear as to what it is I'm trying to do. Okay, so we have 6xy squared. The prime factorization for that is going to be 3 times 2 times xy squared. And then we have 3x cubed y. Well, since the coefficient is 3, we don't need to change that all that much. So it's going to be 3x cubed y. And then 15, the prime factorization for 15 is going to be 3 times 5, x squared, y squared. Okay, now we can find our common terms. We have a 3 in the first term, a 3 in the second term, and a 3 in the third term, so that is going to be included. We have a 2 in the first term, but no 2's in the second or third term, so that is out. And then for the third term, we have a 5, but there's no 5 in 1 or 2, so that is out as well. Now notice that for the x's, we have an x in all 3 terms, and we have a y in all 3 terms. Now we want to figure out how many times each the x and the y appears. Well, here we have 1x, here we have 3 x's, and here we have 2 x's, so that's exactly 1x. That's going to stay exactly the way it is. Here we have 2 y's, here we have 1 y, and here we have 2 y's, so they each share a y in common. So that would just be y to the first. There's nothing to multiply, so this right here is our greatest common factor. And this brings us to our last 2 examples. And this one we have, well, there it is. I'm trying to get myself out to my tray. Okay, here we have 3xy, 5x squared, and 3x cubed y. And once again, we want to find the greatest common factor for these terms. Now, step 1 is to break out the coefficients into their prime factorization, but they're already prime numbers, so we're good to go. We have 3xy, 5x squared, and then 3x cubed y. Okay, so we want to write down the common factors. Now notice that we have a 3 here, but there's no 3 here, so the 3's are out. We have an x here, an x here, and an x here, so the x's are in. Also, each term has this term has a y, this term does not have a y, so the y's are out. And finally, this term has a 5, but it is the only term that has a 5, so that is out. So the only term that is common is x. Let me rewrite that so you can actually read it. There it is. And step Well, actually, step one was the prime factorization. We had primes, so we just wrote them down. Step two was to find the common factors. And then step three is to figure out how many of this common factor we have. And we have one here, two here, three here. So they each have at least one. So we have one. Step four is to multiply all the factors that can be multiplied. There are none that can be multiplied. So this right here is our greatest common factor. And then finally, we have this term, or these collection of terms. 25x squared y squared, 5x squared y cubed, and then x squared y squared. The only one with the first step is, again, to write them in their prime factorizations. The only one that needs to be factored out is the 25x squared y squared, and 25 can be written as 5 times 5, both of which are prime numbers. So we will have 5 times 5 times x squared y squared. Over here, 5 is already a prime number, so that's just 5x squared y cubed. And over here we have x squared y squared. So here we have a 5, here we have a 5, here we have no 5. So we have no 5s in common, so these things would not be included. Here I have an x, and an x, and an x, so we will have an x in our GCF. And we have a y, and a y, and a y, so we will have a y as well. Now notice over here we have two x's, x times x, and we have two x's here, and we have two x's here. So each term has two x's. So we will be x squared. Here we have two y's, here we have three y's, and here we have two y's. So not all the terms have three y's, but each term has two y's, so that would be y squared. And that is step 3. For step 4, is there anything that we can multiply? The answer is no, so this is our greatest common factor. Okay, that is all that I have for the lecture portion. The next portion is to go over a few problems in Hawks. So just stand by and I will get Hawks set up here. And welcome back, and here we are in Hawks, and wait, this is the last question. I don't want to start the last question, I want to start at the first question. And here is our first question. So here we have 70 and 25xy. Well, so we need to do, for step 1 is to do our prime factorization. So 2 factors of 70 is 7 times 10. 7 is a prime number. For 10, we can factor that into 2 times 5. That will give me 2 times 5 times 7, all of which are prime numbers, so that's my prime factorization for 70. Then for 25, well, the factors of 25 are 5 and 5, 5 times 5, both of which are prime numbers, so we have 5 times 5, xy. What do we have in common? Well, they each have a 5 in common. That's it. Everything else is not in common. So in this particular case, our greatest common factor is going to be 5. Okay, let's try some different problems. Okay, well this one looks like fun. So here we have 12xy squared, 60, and 36xy. Now you might be able to tell right away and notice that, well, the greatest common factor here happens to be 12, because 12 times 5 is 60, and 12 times 3 is 36. But we're going to walk through our steps anyways. So if you wanted to factor 12, that would be, if you want to do the prime factorization of 12, 2 factors of 12 are 3 and 4. 3 is a prime number, 4 is not, but that can be factored into 2. 2 2's, 2 times 3, xy squared. Okay, the 60 can be factored into 3 times 20. The 20 can be factored into 4 times 5. And the 4 can be factored into 2 times 2. So that would give me 2 times 2 times 3 times 5. Okay, that's for our 60. And then for 36, well, that would be 6 times 6. And then this 6 can be factored into a 2 times 3. This can be factored into a 2 times 3. We would have 2 times 2 times 3 times 3. Of course, and then the x, y. Okay, so now we want to basically collect the factors that occur in all three terms. So notice each term has a 2. Actually, each term has two 2's. And then each term has a 3. There's a 3 there, a 3 there, and a 3 there. What about the x? Well, there are no xy terms here, so this is out. The y, the same thing. There's no x or y in the second term, so this is out. They are not coming across all three. Notice that in the second term we have a 5, but we don't have one in the first or third term, so that is out. And finally, we have a second 3 here, but we only have 1 3 here and 1 3 here, so that one is out. So this is our these are our common factors. And if we multiply them together, we will get 12, which will be our greatest common factor. And let's put that in there. Let me see if I'm right. 12, enter. I did it right. I know, everybody is shocked. No, we should do this problem right here, because this one actually includes a variable. So here we have 5xy, 15xy, and 25x squared. Okay, well, 5xy is, well, first we want to do prime factorization. This is already a prime number, so we're good here. We want to find the prime factorization of 15, and 15 has two factors, 3 and 5. They are prime numbers, so this becomes 3 times 5 times xy. And then for 25, we have the two factors of 25 are 5 times 5. So this becomes 5 times 5 times x squared. Now notice each term has at least one 5. This one has exactly 1 5. This has exactly 1 5. The third term has at least 1 5. So 1 5 is common through all three terms, so we can write that down. Furthermore, each term has an x. There's an x here, there's an x there, there's actually an x squared there. So each term also, so we can also write down an x, since that's common across all three terms. What about the y? Well, there is a y here, no y here, so this is excluded. Okay, what about the x's? Well, we have one x here, and two x's here. So each has at least one x. So we want to leave this pretty much the way it is. In terms of multiplying, well, there is nothing to multiply. So our final answer here is, so this right here is our final answer. Okay, and then lastly, we are going to do this problem, 42, 60, and 12. Here we have 42, 60, and 12. Well, first step is to find our prime factorizations. Here we have the factors of 42 are 6 times 7. 6 times 7. We can factor out the 6 to 2 times 3. So we have 2 times 3 times 7. 60 we can factor into 6 times 10. Okay, 6 we can factor into a 2 times 3. And the 10 we can factor into a 2 times 5. And that will give us 2 times 2 times 3 times 5. And then the 12 can be factored into a 4 times 3. The 4 can be factored into a 2 times 2 times 3. And that will give us 2 times 2 times 3. Okay, now we can collect our common terms, or common factors. Notice we have a 2 here, and a 2 here, and a 2 here. So we can write down 1, 2. Well, we can write down a single 2. Okay, notice that we have a 3 here, a 3 here, and a 3 here. Here are 3, there are 3, and, well, there are 3. So we can write down a 3. Notice here we have a 7, but there's no 7 anywhere else, so that is excluded. Notice here we have a second 2, and this term has a second 2, but the first term does not, so these will be excluded as well. And then finally we have a 5, but it's only in the second term, there's not one in the first term, or one in the, excuse me, or one in the third term, so this is excluded as well. So, as it turns out, our greatest common factor is going to be the product of 2 and 3. And in step 4, we will multiply these and we will get 6. And that is all that I have for this. Oh, actually, before I do that, let's go ahead and make sure we're right. Let's put a 6 in here, and there we go. And now, that is all I have for this particular lesson. I know I could do a few more problems in Hawks, but many of the problems I did on the slides, I actually did take from Hawks. So if you can do these problems and the ones on the slides, you should have absolutely no problem with the practice and certification in this particular lesson. As always, if you have any questions, please feel free to contact me. This is Bob Boyle, signing off.